right? So 1 mole of oxygen consumed, 2 moles of water are produced. Well, that sounds kind of like I've got oxygen becoming water, right? Okay. The question is kind of vague at that point on deciding it. Really what we're probably doing is saying hydrogen plus oxygen to produce water. And we said 1 mole of oxygen consumed makes 2 moles of water. Well, if I look at the balanced equation, is that equation balanced?
No.
To balance it, what do I need? What's the coefficient in front of the oxygen? What's the coefficient in front of the water? 2. 1 mole of oxygen, 2 moles of water. That first sentence is something you're responsible for being able to find out of a balanced equation. Okay? You have to find that information, pull it out, and use that conversion factor. If you go through and look at everything else within the parentheses, all of those are also conversion factors that you're responsible for knowing where to find. Okay? So that means in exam 2, we gave you a bunch of information that you needed to solve that question because you hadn't learned yet where to find that information. But now that we've talked about where to find that information, what happens to the question? What do we got? 1, 2, 3, 4 lines versus 2 lines. We'll cut it in half because we remove all of the given information. You're now supposed to convert that into the exact same format that you had before to get the same answer. Okay? Yeah, I did pretty well with that. It wasn't horrible. I listened in class. Okay. So with that, go ahead and set it up. Okay. As you go through to do the solve, write down where you're finding that information and how you're getting access to that information. Okay. What steps are you taking? We're not going to pull the whole no alphanumeric or only alphabetic letters in this. Okay. But just try and come up with notes on what step would you need to do first. This is it. What would be the next step? What would be the next step? Where would I find that information to complete that step? How do I identify it? Okay. So process through that. See what you can come up with in 5-ish minutes. And if you got questions on where to start, you can always raise your hand. I can come to you, talk to the people around you, see what you can come up with. Okay. So, where did you start this problem? What do you want as an answer? Step 1, every single time we've solved these, has been to write down at the extreme right what we want for an answer. And yet if I go around and look at what people write, everybody writes down, I started with 9 grams. I don't care what you started with. If you don't know where you're going, that is completely useless. You can be the most brilliant person in a chemistry class. That's awesome. But if you want to be a music major, you're in the wrong class. Okay? It doesn't matter where you start. It matters on where you're ending. You need to realize, have that goal so that you can figure this out. If you don't have that goal, everything you're doing is invalid. So, grams of water is our end. Once we have our goal, now what do we need to know? Where did we start? 9 grams of oxygen. Okay. Ideally, we would look at this and say, the measurement unit. What is the measurement unit? Grams. And our answer? Grams. It's the same. Yippee. I don't have to do any work. What's the substance in the starting material? O2. O2. And our product?
H2O.
H2O. Is the substance the same?
No.
No. So is my answer 9 grams? No. Okay. I have to do a conversion. In the ideal world, what would happen is the grams of O2 needs to disappear from the equation. So I need to place that in the denominator so it cancels out. And in the ideal world, that's an eraser, I would get grams of H2O. Have we talked about a conversion factor that relates the mass of oxygen to the mass of water? Chemical equation. I give you 5 pounds of bicycle tires and 400 pounds of frames. How many bikes can you make? No idea. Why not?
Because we don't know the weight of the individual
Okay.
bike frame.
A formula or an equation does not tell you mass. It tells you the number of those particles. The conversion between grams of water and grams of O2 is not in the chemical equation. It's not there. You can't do that. For the same reason that you can't answer the 5 pounds of frames and whatever number of grams of wheels. Okay? That is a logical misstep. Okay? So now the question is, well, why are you even asking this? When you go through to solve a question, okay, I want to make it from right here, okay, in line with Josh. And I want to move to Ryland.
Oh, that was quick.
Sorry. For some reason, I've got like 4 names that I have to like cross out of my brain for you.
What was the 4 names?
I don't remember what they all are. Jeremy's one of them.
That's kind of close.
I don't ask. Regardless, that's what I want to do. Okay? Here's what I'm getting out of you guys. I'm going to go this way.
Hey, don't do that.
Why would I not do that? I'm going the wrong way.
Yes.
Okay? So what happens when I go the wrong way? I should run into a wall that doesn't work, and now what should I do?
Turn around. Stop going that way.
It looks kind of silly, right? And I'm sure it's great in the microphone. Okay? But that's what you keep trying to do. You keep, well, but I started that way, so I'm going to go that way. If it doesn't work, what should I do?
Turn around.
Turn around. Go back to where I started.
Boo.
Now what should I do?
Go that way.
Ooh. That could have been extra fun. Oh, I didn't get there. So I'm going to go back to where I started.
Yes.
Now what should I do?
Turn another way. Oh.
What's happening?
You found it. You got there.
I got there. I went the long way around, but I'm still there. Okay, that's perfectly valid. Okay, but I'm making valid steps all the way through. I'm not trying to walk through a wall. I'm not trying to do a conversion that doesn't exist. Okay, each of the conversions that we've talked about are things that on their own you've all been like, yeah, that was easy. Stop talking about that. Okay, frames and bikes, frames and wheels to make bikes. Oh, that was so easy. I didn't need to talk about that. Okay, pounds of frames and grams of wheels. Oh, that was dumb. You shouldn't have done that. That was easy. All of these individually on their own are straightforward. You have to be cognizant and thinking about what's happening at each of those steps. Okay? And think back to all of the different things we've tried. Okay? So, grams of water and grams of oxygen. We can say chemical equations. Right? So I'm cool with that because that was a suggestion to use the chemical equation. So let's write out the chemical equation. To get water from O2, what would I need to do? Why am I adding hydrogen gas? What about that equation makes me say I should be reacting that with hydrogen gas?
Reacting with It's
Oh,
in the end.
the question tells me that I should be reacting oxygen with hydrogen gas. Yes, that's where that information is coming from. It is buried in the question. Okay? We have to use that information. Okay? So I now have part of a chemical equation. Okay? So to build a bicycle, I just need a wheel and a frame. I need 2 wheels. Why did you say 2 wheels?
Because bice means 2.
Okay, so we're looking at our product. The product requires more pieces. When we go through and look at this equation, okay, does this equation match that meaning of a bike? Have we balanced this out? No, so what should we do? We should balance it, like we did back in chapter 7. And we should realize that we need those 2's in there. So we can now address the next question. Okay, a suggestion was made that our conversion factor comes from the equation. Okay, so 1 gram of oxygen is going to produce 1 gram or 2 grams of water. So 1 gram of bicycle frames is going to equal 1 gram of bikes. Why is that not true? Let's not even go even that far. Why is that not valid? I take 1 bicycle frame of 1 gram, why do I not get 1 gram of a bike? There's more components. There's other things being added to that. Okay? I have to take into consideration all of those individual pieces. I can't do that from the balanced equation. It's not saying mass. It's saying the numerical amount, the quantity of them, the pieces, if you will. What is our piece in chemistry? Atoms. An atom is a piece. What happens if I take a bunch of atom pieces and I put them together? I have a new piece. What's the name of that new piece? A molecule. So my pieces in chemistry are atoms and molecules. Okay, cool. So I could use from my chemical equation here, not grams, but we'll deal with that in a second. Molecules of H2O and molecules, MLCS of O2. Okay? We've done a conversion like this before and everybody lost their mind. Okay? What is the issue with running this conversion? That, by the way, is a valid conversion, which we will need to use somewhere in this question. Why is inserting it now not sensical?
Because you can't cancel out the grams.
None of the units simplify.
Well, can't you? I mean, you could do it later on. But
Eventually, this will make a lot more sense to insert, okay? But it doesn't make sense now because it doesn't simplify my equation. Okay? So it's up to you. If you want to run with it because you're like, I know I need to do a conversion, then do it. The issue with inserting it now is how do we know to put molecules of H2O on top and molecules of oxygen on the bottom?
Well, we're canceling out.
yeah, well,
You're canceling out what?
O2.
But you're canceling out grams, not molecules. So what's the direct evidence that molecules of O2 should be on the bottom? We don't have a lot of solid evidence. We could run under kind of the assumption that the O2 unit needs to disappear at some point. Okay? So more than likely, my units of O2, whatever that measurement may be, should show up in the denominator. Okay? That is possible. Okay? It's not perfect, but that is a possible assumption I could go through and try and make and work with. Okay? So I'm going to make the statement that while that is a neat conversion, we don't want to do that. Okay? I apologize. Okay? It's a good idea. Not all good ideas lead us in the best directions. Okay? So, back to our conversion. We took a step. We didn't like where that step went.
you ran into a wall.
We ran into a wall, so we need to do something else. What do I want to convert? And now realize I'm saying I want to get rid of the units of grams of O2. That's now my focus. That's why I didn't like the last one. It didn't simplify. Now I'm going to focus on this conversion factor. Right? What can I convert grams of O2 to? Okay. Molecules of O2? Okay. Where do we get the relationship between mass and molecules? Close. Molar mass is not molecules. Molar mass is, nope. Molar mass is the mass moles. This is not moles, this is molecules. I'd be looking for AMU. So what would be my mass measurement? Not grams, but AMUs.
Oh, yeah.
Okay. Does AMUs cancel grams? No, so that's not a good option. Okay, so I don't want to go into molecules. What do I want?
Atoms.
Okay. We could try atoms. Molecules were what?
Multiple pieces.
A piece. What are atoms?
Piece.
A piece. So instead of going from grams to piece, you're going to go from grams to piece.
Exactly. You got it.
Grams to piece in the first case didn't work. What is grams to another piece going to do?
You can do grams to piece technically.
Okay, yeah, we can do it. Okay. What is our conversion?
Well, you would first go grams and moles and then moles.
Okay, so you're making the argument that yes, we can make this conversion. We don't have a direct step. You're saying to go grams to moles. Why are you saying moles? We'll come back to that. Why is grams to moles better than grams to molecules?
Well, because then you can go from moles to molecules.
I can go from moles to molecules. Okay, why grams to moles and not grams to molecules?
These moles is a quantity, not necessarily.
Do we have a conversion factor between grams and molecules? No, that does not exist. Do we have the conversion factor between grams and moles? Yes. Okay. It's recognizing the conversion factors we've already talked about. Where is the conversion factor found for grams to moles?
Periodic table.
The periodic table. So I would look at the mass for oxygen, which is 16. If I write 16 in there, what happens?
It's wrong.
It's wrong because
It's 2,
there's 2 oxygens. It's not 16, that is
32.
32. Okay? And I keep hearing reference to AMUs. Okay? If you wanted to do so, by all means, we could have done that. We could have gone grams to AMUs of O2. Okay? So we're going to set this up. We're going to run these in parallel. Where's our conversion between grams and AMUs found?
On the front of the page, probably.
Front of the exam, it's a
Yeah.
given conversion factor, or it's one that you memorized.
66.
1.66 times 10 to the negative 24 grams is 1 AMU. Is that a valid conversion factor?
Yes.
Yes.
Yeah, perfectly valid. I have no problems with that conversion factor. All right. And what happens? Grams of oxygen cancels. Cool. Yes. Okay. I'm now in AMUs of oxygen. Did that get me closer to the answer?
Yeah, technically a little bit. You
Because you
can
can
go
go
now do
AMU
AMUs
to
to
grams.
moles.
Oh, no. Yeah, you can. No.
Okay.
No, no.
The substance didn't get me closer. The measurement was grams, and instead of being a gram measurement, I went to
Oh, you went backwards.
AMUs.
That's true.
Right? It's still a mass measurement.
Because you want to go AMUs to moles.
I'm not getting any closer. I'm also not really getting any further. Blame Braxton later.
It's not a,
Now what? What unit will we
Yeah,
have?
it's good to know.
just go back to the grams and moles.
I appreciate you get it. and putting it
AMUs.
back, 'cause now
You need to see what happens when you use the wrong thing.
So we could think
AMUs of O2. Is AMUs of O2 what we want for an answer? No, what do we want?
H2O.
We want grams of H2O, right? Is there a conversion factor between AMUs of O2 and grams of H2O? No. So what can we do?
Go back to the grams.
bottom.
Okay. We could go through and do the bottom. Sorry. You need to make the top work.
Okay. We could,
It does. It absolutely does work. Sorry, it does.
Okay, now you can do.
we could
You
do,
can do AMUs back to grams and then grams to moles.
yeah, we could.
Okay. What can I convert AMUs to? As a hint, how about molecules of O2? Remember the thing that you guys wanted at the very beginning? You asked for
You can.
molecules of O2. Can I do that conversion?
Sure.
Yeah, what is that conversion?
It's 1.
AMU was what?
It's a mass.
A mass measurement. For what? For a molecule, right? Where do I find the mass unit for AMUs and molecules? Periodic table.
32?
32 AMUs is 1 molecule of O2. Yeah,
Damn.
cool. We did a conversion. Okay. I now have molecules of O2. Right? As was suggested earlier by Josh, didn't we have a conversion factor that involved molecules of O2 before? And we said, well, I don't want to use that yet. Yeah, we did. Yeah, that was a pretty awesome job you had. Where we converted molecules of O2 into
Oh, that is H2O.
molecules of H2O. And we could do that conversion factor because we had the chemical equation. Right? Where we know 2 molecules of O2 was 1 molecule, or 2 molecules of H2O was 1 molecule of O2, yeah?
Yeah.
We did it.
Okay. Did we do it? Are we at our final answer?
Almost.
Son of a... Okay, well, keep going. 2 molecules of H2O, grams of H2O. Are those the same unit?
No.
No.
You gotta cancel out molecules.
We're going to run out of space here. Molecules of H2O. What do I want to convert to? Ideally, grams of H2O. Is that a direct
No.
conversion? No. Dang it!
Molecules to AMUs, AMUs back to grams.
Okay. What is our conversion factor? Where is that conversion factor found?
One.
Where do we find information about the
Periodic
AMUs?
table.
Periodic table. 2 hydrogen being a mass of
1.01.
2. And oxygen. 16.
16.
18 AMUs for 1 molecule of H2O.
And then back to
What unit would we now have?
AMU.
AMUs, you know.
AMUs, we need grams, so what do we do?
To convert that into
AMUs to grams, how do we do that? 1.66 times 10 to the minus 24th grams is 1 AMU.
Yeah.
And we would now have, hallelujah, grams of H2O with so little space in my conversion that I can't even fit the final answer on there. Okay? But I could now punch it in the calculator and I could get a final answer. I may have gone the long way. We may not even see that yet. Okay? But I have the correct unit. I'm using conversion factors that I'm aware of, that I can use, and I will continue to use them as I punch my way through this. Okay? Let's go back to the bottom route. Okay? For every scoop of peanut butter that you put on the bread, you open a new peanut butter jar. That's what you just did. It's still a peanut butter and jelly sandwich that I'd probably eat.
Really love peanut butter.
You just wasted peanut butter, right? Because you've got like 5 jars open.
It's not a waste. It is efficient use.
get the answer.
Grams of H2O at the bottom. What unit would we have for the bottom?
We got all.
We had moles of O2. Is moles of O2 what we want for an answer?
No.
No, we want what for an answer? Grams of H2O. Can I convert the moles of O2 into grams of H2O? No. What could I convert? What's that?
Moles of H2O.
I could convert moles of O2 into moles of H2O. How do I do that? What is a mole?
Something around 40 years.
6.022 times 10 to the 23rd what? Atoms, particles, molecules. A mole is the same thing as a molecule. It's just a really large number of molecules. It is 2 to 1. Where'd you get the 2 to 1 from? Your chemical equation. That is a valid conversion factor. Your chemical equation can give you single units. It can also give you any scalar factor. What is a mole? A scalar factor. It's just scaled it up by a much larger amount. That's the power of the moles. What unit are you now in?
Molecules.
No.
Moles of H2O.
Moles of
You
H2O.
said molecules.
I did not say that.
Said it was.
I said molecules are equivalent to moles as a substance. Moles is 6.022 times 10 to the 23rd molecules.
I'm just testing you. We got it.
Moles of H2O. What do I want? Grams of H2O. God, when do I want it? Now. Where do I find the conversion factor between grams and moles? The periodic table. And I get 18 grams of H2O is 1 mole of H2O. This bottom calculation looks really similar to what was done above. 9 divided by 32. Our second calculation, what do we do? Divide by 32. Times 2. Times 2. Times 18. Times 18. You mean the two things that we did, both top and bottom, are the same?
Yeah, we just added the.
Yes. You added a step
Just to cancel it out.
to get molecules. You wanted You looked at the periodic table and the only thing you remembered on the periodic table was that it told you AMUs, so you wanted AMUs. That's cool. If that's all you remember on it, then you get to do this conversion. What happens at the very end? You undo the conversion you already did because you're not remembering what I told you the power of the mole was. The mass is not the atomic mass only. It is also molar mass. And the molar mass relates what to units? Moles and mass. Hence the term molar mass. Amazing. The language tells us some information about it. Yes. Right? It can allow us to simplify through. Okay? We are responsible for knowing where to find each of those conversion factors. We've talked about them in great depth. Okay? And this is the next big part that I've talked about with the standalone class a lot. Okay? Your success for a single conversion, because you've been doing it in your head and not writing it down, is not bad. It's about a 90%. If you get a 90% on the exam, are you going to be happy? Yeah, okay. We just did 3 calculations here. 90% times 90% times 90%. It's 0.9 times 0.9 times 0.9. I see a calculator. Can you give that to me? You just went from a single calculation. You know how to do each of those conversions. Awesome. At A level. But now when we string it together, what happened? You went from an A to a C in one question because you did not write it down. That was it. That was literally it. You did it in your head, and there's that 10% failure rate. That 10% failure rate compounds all the way through. Okay? I heard a couple people say, well, I didn't say I was getting an A on it. Okay, fine. You aren't starting at a 90% success rate. You're starting at a 70. 0.7 times 0.7 times 0.7. Nicole, can you give me that one again? You're starting now at a C level, and I can't do the math, so I'm not going to.
Error compounds like interest.
0.7 times 0.7 times 0.7 is not 0.21 maybe.
0.7?
0.7 times 0.7 times 0.7 was 0.344. Okay. So you started at a C. You started at a C and you dropped to roughly guessing on the exam. Okay? And that's the problem I'm trying to address. What I'm trying to do here is not give you something that makes you have all this extra busy work. What I'm trying to do is insist that if you're starting at the 0.7, your 0.7 is consistent all the way through, you get a passing grade. Okay? If you refuse to write this down, you're now stringing those calculations together and you're dropping to, let's not do more analogies, not passing the class. Okay? Please, just write it down. Even if we wrote it down the wrong direction, what happened? We still got it right. Okay? Each of those conversions is something that you are aware of, you know how to do. They are simple. Okay? But putting those simple conversions next to each other compounds your error. Be careful with that. Which sets us up with the next system. Because you need to prove to me that you can do it, we have 4 questions. 1, 2, 3, 4 questions. Pick any of those 4 you want. Work on it for the next 5 minutes. Okay? If you get one solved, then go ahead and move on to another one. Okay? 4 questions, 5 minutes. Can people do these calculations in your head? Yes. I don't care. Write it down. Right? When Greg asked you to do free writes, this is our equivalent of a free write. Free write the solve.
Work non-stop till it's done.
So because I don't have a lot of space to write here, I'm going to start with question number 1, but I'm going to have to erase the equation to go through and do this. Almost invariably, every section I'll get a significant number of people be like, ooh, sodium? I can't answer this question about sodium because I don't see sodium in the equation. There's no sodium in the equation. So I can't do that. I'm going to skip it and move on. Okay. Number 1, by all means, you look at a question, you're like, I can't answer that, move on to the next question. That is perfectly fair game. Okay. The next part is you now have time at the end of the exam. You can't move on. Finish the freaking exam. Go back and make some solid stab at it. What do we want for an answer?
We want atoms of sodium.
When do we want it?
Now,
After 1 conversion. I agree. 1 conversion. What are we starting with?
molecules of sodium carbonate.
How many molecules of sodium carbonate are we starting?
1 molecule of sodium carbonate.
1 molecule of sodium carbonate. Yeah, sodium. Just sodium at the end. This is going to be a doozy. I don't know. I can figure this one out. So ideally, this molecules of sodium carbonate needs to disappear, right? So it's got to show up in the bottom. Make sense? What do I want to have show up on top?
Molecules of sodium.
Okay, we could say molecules of sodium. Molecules doesn't really make sense because
Sodium is it's our atoms.
it's a single atom, so it doesn't make sense to say molecules. I should actually say atom. Okay. Yeah, you should. Dang. It's a little snarky. So now we look at this. Ooh, atoms to molecules. I can't do that. All right, so let's rephrase it. How many atoms of sodium are in molecules of sodium carbonate? 2. Where are you getting this 2 from? Because I'm hearing you need a chemical equation. What's that, Rylan?
Because you see it with 2 after Na2. It can't be that easy.
If we look at the formula for sodium carbonate, how many sodiums are in that formula?
Chemistry works.
That's not it.
Chemistry doesn't work that way.
When you said 2, you were.
Is it really that simple? Yes. Yes, it is. Absolutely.
It's just stupid.
The information is there. You have to do that interpretation.
That's not fair.
So not fair, right? You're asking us a chapter 8 question when we're talking about chapter 9. I already learned that. I don't have to learn it again.
Yes.
Doesn't work that way. Right? So, that's not erasing. There it goes.
Leo says grr.
Jeff says curve.
So we'll erase question 1 just so we can ignore that. That was rough. That was painful. Okay. 2. What does 2 ask for?
Molecules of sodium carbonate.
Are needed to make what? 2 molecules of sodium hydrogen carbonate, right? So what am I given as starting information?
Sodium carbonate.
What am I given as starting information?
Oh, sorry.
Molecules of sodium hydrogen carbonate, and I'm given 2 of them. So I set up my conversion, and I want molecules of sodium hydrogen carbonate. What do I want that to do? That needs to disappear, so I'm going to put that in the denominator. What am I going to put on the numerator? I'm going to write molecules of sodium carbonate. Why am I writing molecules and not moles?
You want molecules.
The answer I want is molecules of sodium carbonate. Okay? The process is always write what you want. Okay? You may not have that conversion factor, and that's a separate issue. Okay? But always write what you want first. Okay? Because otherwise you're like, oh, I think I got to multiply by the molar mass. You just did that in your head. You have no clue what you're doing. You're throwing numbers at it and hoping for the best. By writing down the units, you can now try and track and say, is that a valid conversion? Okay, so is there a relationship between the molecules of sodium carbonate and the molecules of sodium hydrogen carbonate?
They're just friends.
You simply added some hydrogen.
How did okay, there's an interesting observation. I just added some hydrogen to it. How did I add the hydrogen to it?
There's one for one.
Where did I get the hydrogen from to do that? I'll kind of accept the equation. What in the equation gave the hydrogen? The H2O. Was that it? I just needed to add H2O? No, I also needed to add CO2. I now have a chemical equation that tells me how I got that extra hydrogen, how I changed that molecular structure. What is the coefficient in front of sodium hydrogen carbonate in my equation? 1. What is the coefficient in front of sodium hydrogen carbonate? 2. How do I convert those two? I take one molecule of sodium carbonate, I combine it with one H2O and one CO2. Mixing pot, magic, poof. 2 sodium hydrogen carbonate. Yeah, 2 sodium hydrogen carbonates come out of it. There it is. That's all I had to do? Yeah.
That's it?
That was it. You now have your answer.
So it's just
How
one?
do we go?
Only 2 is easier
How
than
do we
1.
go from complicated to simple?
Come back to that in a second.
So, I just want to, this kind of goes back to the wheels and frames thing. We're only being asked to solve for one, based on one of the criteria.
One
of the
criteria.
equation. We're not, if it said, given so many molecules of H2O or something along those lines, we would have to then go back into the equation and do a second
Yep.
limiting factor.
So all this is saying is I'm going to convert sodium carbonate into sodium hydrogen carbonate. Okay. To do that, I have to know how to do it. To make a bicycle, what do I need to know? I need to know that I need a frame. I need to know that I need 2 wheels. That information for you guys is intuitive because you've seen bicycles and you roughly know you have those pieces. The chemical equation is the same thing. Right? It isn't any different. The only part that kind of confuses people is we have to build this kind of symbology around it with letters and numbers. And it's that meaning that we tend to lose track of. Okay? That's why we started all the way back with nomenclature. How do we build these molecules? Okay? Or with atoms. What is an atom? What can we do with those atoms? We can make molecules. How do I take those molecules out into the real world and work with them? Okay? You've done that building bicycles. Even if you didn't build a bicycle, you can visualize it and see those pieces. We can't do that in chemistry. That's why we start with our pieces and slowly build our way up. We're now looking at the mathematics on how many we can produce out of this. Kinda? Okay, you had a question.
So where did you get the 2 from then?
Where did I get the 2 from? Which 2?
Was it just the one on the bottom?
2 molecules of sodium hydrogen carbonate. Where did I get that 2 from?
Is it just from... Okay.
There's our sodium hydrogen carbonate. The 2 came from the coefficient front. That 2, for whatever the spacing is weird on that, and everybody seems to miss that 2. But that 2 is there as a coefficient. Every time you've gone through and done these, you've done them correctly. Okay.
Yeah.
Wait, what?
It's okay, Mike.
It is absolutely my fault. Let's take a look at question 3.
If you don't get a question, Mike.
How many moles of CO2 are necessary to make 1 mole of sodium hydrogen carbonate?
Hey, Mike, you don't get a question.
Oh, yeah. Oh,
So
shoot.
if you're going to multiply it on the previous problem straight across, so it's 2 times 1, which is 2, divided by 2.
Mhm.
2, yeah, so how do you get 2?
I didn't solve it. 2 times 1 divided by 2 is what? 1. What's the answer? 1. Yeah. What she was asking about is where did that 2 come from? Not that the answer was 2. Okay. What's the next one say?
How many moles of CO2 are necessary to make 1 mole of sodium hydrogen carbonate?
Do we need moles of CO2?
What are we starting with?
1 mole of sodium hydrogen carbonate. 1. We need to get rid of that.
What happens?
You gotta cancel that out.
Moles of sodium hydrogen carbonate change, right? And I want moles of CO2. Why is this question different than the previous 2 questions?
There's moles.
We're using moles, but what is a mole?
Just a large
Just a large number of molecules. Is that large number different for individual substances? No, it's the same. It all scales exactly the same. Which means I could go up to my chemical equation, and instead of that being one molecule, I can now call it 1 mole, which would then mean the water is not 1 molecule, it's 1 mole. Which would mean the CO2 is now, would mean the sodium hydrogen carbonate is 2 moles. All we're doing is just shifting the unit based off of that multiplicative factor, and as long as it's consistent, we're okay. That's why we picked Avogadro's number.
So 1 mole of CO2 equals 2 moles of NaHCO3?
1 mole of CO2 is 2 moles of sodium hydrogen carbonate, and our answer becomes
Oh, I'm sorry.
half a mole of CO2. Why did we have to switch it into moles?
So that we could,
Because you can have
so we could use 1/2.
I'm allowed to have half a mole of CO2. If I'd done it as molecules, this question doesn't work. I can't end with a half or start with half a molecule of CO2. We have to be in units of moles. Right? Last one. What?
No, you could solve it because it was a mole.
Because it was moles.
Because it's just, you said you can convert them all to moles, and it's just the equation written out in word form.
I appreciate that.
That was me being proud of you.
I want moles of sodium hydrogen carbonate. What am I given?
Sodium carbonate, a mole of water.
That's not carbonate.
That's what? Whoa.
Whoa, what do you mean, whoa?
What does that say?
It says mole of H2O.
Plus?
Yeah, plus, can I do that?
Yeah.
Can I add in my conversions?
Yeah, I guess so.
Those are all
You would just kind of,
No, at no point have we added. That's not going to make sense. Okay? If I take 2 bicycle tires and a frame, I get 3 bicycles. 2 tires, 1 frame, and I get 3 bicycles. Because 2 plus 1 is 3. No, that doesn't make sense. Okay? So I can't add those. So what am I doing?
You're multiplying.
Okay? So I'm going to multiply by moles of H2O. But I don't like moles of sodium carbonate, so I'll put that in the denominator, right? So that that unit cancels out.
No.
What numbers would then go in there? This will be an interesting question.
Oh, that would,
That would be 1 in those. Is that 1
no.
the same as the 1 in our question? Why not? And don't tell me 1 is purple and 1 is red.
one's boxed.
Repeat that question. Is the 1 in our conversion factor, 1 mole of H2O, 1 mole of sodium carbonate, the same as the 1 in the question?
Yes. I think so.
Well, there's no carbon dioxide, so that's what you're trying to get at then. No.
No. They have entirely different meanings. What is the 1 in the question? What is the 1 in the question? The mole of what? That's doing what? That I have mixed. Yes. What is the 1 in red in my conversion factor? Where did I get that from? From the chemical equation. The chemical equation has nothing to do with me. That's me describing what the world is doing. Right? That's like me saying, I'm going to say there's gravity. Ta-da, there's gravity. That's my fault because I said there's gravity. No. I've made an observation of it. The conversion factor of the ones in red here, those are observations of the world. What's the purple one? Me mixing chemicals. Those have entirely different meanings. Okay? Similar number, just because the number's the same doesn't mean the meaning is the same. Okay? What would our answer be with the conversion as written? Numerical answers are going to flip me out, so let's just rewind, let's take a step back, recenter. Numerical answers are a bad answer. Don't give me numerical answers for the answer for the question as shown. I would have moles of H2O. What answer am I aiming for? Moles of sodium hydrogen carbonate. Did I do anything useful to getting to my answer? No, that was pretty awful. What do I actually want in the numerator? I want sodium hydrogen carbonate. Why do I want that?
So you can end with it?
That's what I'm trying to end with. What numbers should now show up in that
Bottom?
conversion?
2 over 1.
Why is it 2 over 1?
Because
For every 1 mole.
This says 1. I don't believe you. Why are you saying what? Why are you like, oh,
Because the
yeah, why am I getting the 2? It comes from the chemical equation. That's not given information, that's chemical equation. Okay? The 2 comes from the chemical equation. You have to recognize that these numbers will and potentially overlap. Match their meanings accordingly. That means I would get 2 moles of sodium hydrogen carbonate as a product. In that conversion, have I evaluated the water? Did I evaluate the CO2? No. Could I have added different amounts of water and CO2?
No, because you went to the same product.
Potentially. Okay. You're saying no because?
It went end in the same product.
I don't quite accept that answer. Regardless of the amount, I will always make sodium hydrogen carbonate. What will change? Regardless of the amount of wheels and frames, I will always end in bicycles. What changes when I change the amounts of the wheels and the frames? The number of bicycles. If I change the numerical values for the moles of sodium carbonate, water, and carbon dioxide, does that change my answer? That changes the numerical answer. I would then have to compare those numerical answers to verify one way or another. If they're the same, then it doesn't matter. If they're different, I have to pick the smaller of those values. That is a limiting reactant concept. 3 frames, 3 wheels, let's do wheels, because that's a W. 3 wheels, 2 frames. How many bikes can we make? 1. Why? I had 2 frames. The frame needs 2 wheels. I don't have enough wheels to make 2 full bikes. I end up evaluating the smaller of those numbers. I had to run 2 separate calculations. One for the wheels, one for the bike, or one for the frames. Here, instead of having 2 parts, how many parts do I have? I have 3 parts. I have sodium carbonate, I have water, I have carbon dioxide. I have to check every single one of those parts. Which means I go back up here and I say, well, what if I started with moles of, what am I starting with? Water. What was that?
What?
Sometimes you just need to breathe. What do I want to end with? Moles of sodium hydrogen carbonate, right? Where do I get that conversion? From the chemical equation. That chemical equation says this is 2 to 1. How many moles of sodium hydrogen carbonate would I get? 2. Is there a difference between those numerical answers? No. So the moles of sodium hydrogen carbonate I can produce is 4.
No,
Why not?
because you just, yeah, it's not. It's just not.
Stupid English language not helping me out. Once we've made 2, we've run out of reagents. We can't make more. We're not adding those up. We can't add those results.
It doesn't matter if you have an excess of 1, you need.
That's the most that I can make. That's the end result. That's what determines it. Okay?
What about target?
We're not going to look at the third one. You should be able to do that. The last question here was one we've already done. Okay? Where I actually want to get to is in this concept vaguely of water and solubility. So we're going to whip through this because this is kind of not a big deal. Water is the bent structure. Water has special properties. What are those special properties?
It's known in all three phases.
Yeah, it is all three phases, yeah. Because it has that bent shape, it becomes a polar molecule. Why is it polar? Yes, because oxygen is more electronegative than hydrogen, which means the electrons in the bonds between the oxygen and the hydrogen spend most of their time where? With the oxygen. So oxygen has effectively gained electrons, making it negatively charged. Where did it get those electrons from? The hydrogen. So the hydrogen lost electrons, it became positive. That would start to make this look like an ionic structure. We know this is not an ionic structure because the airplane crashed. We did not survive that. That was unfortunate because we remember what our bond classifications are. We have 3 classifications, 2 of which you're formally aware of, ionic and covalent. You know you have an ionic bond because you studied nomenclature and you can now name everything. And you know you have an ionic compound because non-metal and a metal. And we look at oxygen and hydrogen because all the way back in Unit 1, we know that oxygen and hydrogen are non-metals because they're to the right of the staircase. Wait, hydrogen acts like a metal, but it is not formally a metal. It is still a non-metal. We have a covalent bond, which means I cannot show formal charges because those charges say that it's an ionic compound. But the oxygen is still gaining electrons, just not formally gained. So I need a notation to suggest that oxygen has started to get negative, but isn't there. It's changing its charge. Is there a symbol that we've used to represent a change? Delta. So if I put in a delta, we'd be okay. The issue with that delta is, what does that capital delta mean? Heat, temperature. So I can't use that symbol because it's already used. So I'm going to use a different delta. I wonder if we had a different delta. Like, how about capital and lowercase?
Of course.
And we have our delta notation. That is a lowercase delta as best as I can draw it. Not an 8, not a what?
A Q upside down.
It would be a G.
Really? Or like backwards also?
I'll say that if that helps you remember it.
Sure, stick with that. Okay, we now have the delta notation. The other bond is doing the same thing. What we end up seeing is a net positive between the hydrogens and a net negative, or the electrons moving towards the oxygen. We've now drawn a dipole arrow. Those partial charges are what contribute to all of the activity of water as a solvent. That's what makes it cool. Okay? That's how we can dissolve compounds in it. And that's our salts. That's how we can see solubility curves, which I'm way too late, so we're just going to stop while I'm not ahead. And hope we can get further ahead with that